So the gravitational force. Now this gets quite interesting because Newton figured this out using Kepler's laws. You don't have to know that, but the way he figured it out was quite genius. And his formula actually laid the groundwork for someone to figure out the gravitational constant. So Newton's law of gravitation. So he proposed that every two objects with mass attract each other with the force. And this is the formula right here. And I have the formulas memorized. So the force that one object I forgot what it's called. That one object attracts, I guess. We'll use attraction. The force of attraction. Typically forces are used to repel, actually. But actually, no, that's not true because yeah, okay, anyways. So this force here is defined as gm1 m2 divided by radius squared. And this shouldn't be radius, but we'll get to why it's radius in a little bit. The gravitational constant is 6.674 times 10 to the negative 11th, meaning that it's quite small. I mean, 10 to the negative 11 is 1 times 10 to the 11th, which is a lot of zeros. Basically, it's a really small constant. That makes it so when there's someone heavy next to you, they won't attract you as much. Or if you're next to a heavy machinery, it won't do much. There's barely a gravitational force there, and that's because of this gravitational constant here. I'm not too sure how they figured this out. I should probably research that, but this is just a gravitational constant, and it's kind of like a curve fit. I mean, not really a curve fit, but it makes the rest of the equation work. So this is an action-reaction pair. Newton's third law. Each object pulls on the other, but opposite directions. So let's take the Earth and the Sun. And we'll say this is the Sun. There should be two other planets here, but I'll just abstract them for the sake. This is an orbit. So using the gravitational force formula, it would be the gravitational constant, which is 6.674 times 10 to the negative 11th. The mass of the Earth's sun, in kilograms, by the way. We're always going to be dealing with kilograms and meters because of the metric system. So it would be mass of the sun. I'll denote that as mass ms, and then me, which we'll get to this one later, actually, and r squared. So note that the force, if we plug this into the formula, the force that the sun is attracting on the Earth is also attracting the force with the same way. So if the sun wasn't as massive, which you could watch our previous video, remember the force equals mass times acceleration formula, with a higher mass, it requires a higher force to achieve the same level of acceleration. In simple words, since the sun is way bigger, it won't move as much as the Earth, and that's why the Earth is constantly rotating, along with the celestial bodies obviously next to it. But the point being is that they are attracting the same force to each other, and that's just Newton's third law. For every reaction, there's an equal and opposite reaction. For every action, there's an equal and opposite reaction. So the sun is exerting the same force as the Earth, and that's just the logic behind it. So, yeah, but only the Earth moves because remember the formula F equals ma. Since the sun is so massive, like let's just assume it's 999 times the Earth's mass. I'm not really sure if that's accurate, and let's say the force is like 1,000. That means the sun is moving at 1,999 of the Earth's. Wait. 1,999. Sorry, let's just say 999. That means the Earth is moving, or sorry, that means the sun is moving at a way slower speed than the Earth, or it has a way slower acceleration, should I say? So that's the logic there. But this gets interesting in a little bit, actually. So I don't think I mentioned it here, but that formula was first applied as for 2 points in a plane. And notice that it has to be small enough to be a point on a plane. And that's kind of illogical because a point in any Cartesian coordinate place takes up no space and no dimension. But we know that the Earth takes up space, and the sun also takes up space, and the moon also takes up space. So how did the scientists resolve this? So, what they realize is that if something is big enough, to be a sphere or circular shape, then we can simply just measure the center as a dot technically, because as we zoom out, it'll look like the center. So technically, the center is all we're focused about, and let's say this is in radius of x, and that simply goes there as x squared gravitational constant times the mass of this celestial body. We'll say it's Earth, so it's ME, and then we'll say that I'm a person standing on the Earth right here, M2, and that is the force the Earth is attracting me towards. X is the Earth's radius, because again we're looking at this as a spherical model. So the mass is centered at the middle, and that's how we calculate the radius. So the radius will always be the distance from, I mean, you guys know math. The distance will always be from the center of the circle to the end. And since planets are pretty much spherical, we can assume them as a point in space, and we'll use the center as it. So then if we do a little bit more extrapolation, and we'll say that there's a celestial body here. So like, let's say this is the Earth and this is the Sun, which it's not obviously drawn to scale because the Sun is like 100 times bigger. Or actually, I don't know. Let's measure this distance as y, x, and r. The radius or the distance between these 2 points would be x plus y plus r, because we're measuring the mass at the center of the bodies, and that's how we do so. Newton proved this with calculus, I believe. So, weight is just a force that something is exerting towards you. So technically, it would just be this formula here. This is literally the weight formula. But if you want to simplify it, gm1 over r squared is just gravity, which everyone knows is 9.8. Here's the squared. Negative, if you're assuming downwards, is a negative force. So we can simplify this entire part to gravity. So that's where we get the F equals mg formula, which looks quite similar to the force equals mass times acceleration formula, because gravity is just an acceleration force, and these two are the same. So you can actually prove this because remember, force equals mass times acceleration. So mass times acceleration equals gm1 m2 over r squared. Divide m on both sides, so a equals g m1 m2 over r2m. And remember, this would just be m2 because we're calculating the force of the person, or how much. Well, technically, the force you're exerting on the Earth is the same force the Earth is exerting on you. So same thing, I guess. But you just cancel it out, giving us the force of gravity here. So simply put, this is the weight formula. It's the same exact thing as Newton's second law, just that the acceleration was replaced by gravity. So this is nothing new. Everyone should know this already. So yeah, why weight changes but mass doesn't? Well, look at the formula here, the gravitational constant and everything. We have gm1 m2 over r squared. Notice that r squared is in the denominator, meaning the higher this one gets, the smaller that this will get. So simply put, the farther away two objects are, the weaker the gravitational force is, which you should know already. I mean, that's why we're not getting I can't really find an example to think of, but simply put, as you get farther away, the gravitational force gets weaker, and the smaller of an object you are, the less force is being exerted on you. So a feather and me, the Earth would be exerting way more force on me. But that's not to say that they wouldn't fall at the same speed in a vacuum. Me and a feather would accelerate at the same speed down towards Earth. It's just that there's less force on the feather. So mass is how much inertia an object has. It never changes. Mass is constant. So that's it.